Okay, so everybody loves a good time travel story, right?
Absolutely.
I think it's one of those things we've all kind of sat around and thought about, like,
Okay.
what if I could go back and see, the pyramids being built or travel to the future and see
Yeah,
what's coming.
for sure.
So today we're going to deep dive into the concept of time travel and look at what the science actually says about the possibilities.
Sounds good.
So I think a good place to start is with the idea that in a very real sense, we're all time travelers.
Yeah, oh, yeah.
Every second that goes by, we're moving forward in time.
We're moving through time.
Right. And that might seem kind of obvious,
Mm-hmm.
but it's actually a really important concept to grasp when we start talking about the more mind-bending aspects of time travel.
Yeah. It all starts with that basic idea that we're always moving forward in time.
Yeah, and I think a lot of people tend to think of time as this kind of like abstract thing,
Yeah.
right? It's just this thing that's always ticking away in the background.
Just kind of there.
But in physics, the current understanding is that time is actually a dimension.
A dimension of the universe?
Yeah, it's woven into the very fabric of the universe, just like the three spatial dimensions that we're all familiar with.
So, we have left, right, forward, backward, up, down.
Yeah.
And then we have time.
Right. And together, those four dimensions make up what we call space-time.
It's space-time.
Right. And so our experience of time passing, that feeling of moments flowing from the past to the present to the future, that's essentially us moving through this fourth dimension, this time dimension.
Exactly. We're moving through the time dimension just like we move through the spatial dimensions.
Okay, so we're all constantly in motion through time.
Yeah.
But there's this weird thing about time that makes it different from the spatial dimensions.
There is.
Right?
Right.
We can move freely in space. I can walk forward. I can walk backward. I can go left. I can go right.
Yep.
But with time, it feels like we're stuck on this one-way street. We can only go forward.
Exactly. It's like a river. We're just flowing down it.
We can't just decide to, stop time or rewind it or fast forward it. It's like we're trapped in this constant forward flow.
It feels that way, yeah.
Yeah, and this is where things start to get really interesting because our sources suggest that this feeling of time as this relentless, irreversible current
Right.
might actually be more of a perception than a fundamental reality.
Or of a perception, yeah.
And this is where we bump into one of the core principles that kind of underpins all of this discussion about time travel.
Okay.
The idea that everything in the universe,
Everything.
every single thing from the tiniest subatomic particle to the most massive galaxy
To the entire universe itself.
yeah, is constantly moving through this four-dimensional space-time at the speed of light.
At the speed of light.
Wow. Yeah, that's the speed limit of the cosmos. You can't go faster than the speed of light.
Okay, so we're all moving at the speed of light through space-time.
Yeah, it's like we all have this speed budget.
It's a speed budget.
Right, and we can spend that budget on movement through space or movement through time.
So if you're standing still, you're using all of your speed budget to move through time.
Yeah, and if you're moving really fast through space, like close to the speed of light.
Then you're using more of your speed budget to move through space.
Right, and so you have less left over for movement through time, which means that time slows down for you relative to someone who's not moving as fast.
Relative to someone standing still.
Yeah, let's try and make this a little more concrete with an example.
Okay.
Imagine you're sitting at home on your couch.
Just relaxing.
You're not moving through space at all, right? You're just sitting there.
Not even an inch.
But you're still hurtling through time at the speed of light.
You are.
That's your speed budget being used entirely for time travel.
All time travel, no space travel.
Now let's think about the opposite end of the spectrum.
Okay.
Let's think about light itself.
Light. Interesting.
Light is made up of these tiny little particles called photons.
The photons. Yeah.
And photons travel through space at the speed of light.
Always.
Right. That's their thing.
The speed of light.
Yeah, that's their whole deal.
It's their jam.
So because they're moving at the speed of light through space, they have zero speed budget left over for movement through time.
So they don't experience time at all.
Right. From a photon's perspective, time doesn't exist.
Wow.
It's like they leave the sun and arrive at Earth instantaneously.
No time passes for them.
Even though from our perspective, it takes about 8 minutes for light to travel from the sun to Earth.
It's wild.
Yeah, that sunlight that's hitting your face right now,
Right.
those photons have experienced zero passage of time on their journey from the sun.
So it's brand new.
It's wild, isn't it?
Yeah, it's a completely different experience of time.
Yeah, so we've got these two extremes, right? We've got us sitting still, moving entirely through time,
Mm.
and we've got photons moving entirely through space,
At the speed of light.
and everything else in the universe falls somewhere in between.
Somewhere in between.
You know, we're all moving through space and time to some degree.
Using up our speed budget in different ways.
Right, and this idea that our movement through space and time are interconnected like this, that they're part of this constant speed through space-time.
Yeah.
This is the foundation of Einstein's theory of relativity.
It is.
And it has some pretty wild implications for time travel.
It does.
Now, we should probably acknowledge here that the examples we've been using are a little bit simplified,
Sure.
right? The idea of being absolutely still relative to all of space,
Yeah.
that's a pretty complex concept.
There's no absolute frame of reference.
Right, and defining a reference frame for photons is also tricky.
Yeah, those are nuances of relativity.
Yeah, but for the purposes of grasping this core idea,
Yeah.
the interconnectedness of our movement through space and time, these examples are, I think, pretty helpful.
Yeah, they illustrate the point.
If you want to really dig into the deeper complexities of relativity,
Mm-hmm.
there are a ton of great resources out there.
Lots of books and articles and videos.
You know, you can really go down the rabbit hole with this stuff.
It's fascinating stuff.
Yeah, it is. So we've established that we're all moving through space-time at the speed of light.
Yep.
And we can kind of redistribute that speed between our movement through space and our movement through time.
Right.
And this brings us to what our sources call real and easy time travel.
Real and easy time travel.
Emphasis on the easy.
At least
in direction.
in one direction.
Yeah, in one direction forward.
Forward in time.
So the first way to travel to the future that our sources talk about
Okay.
is something called time dilation due to relative motion.
Time dilation.
Yeah, and this basically means that if you're moving really fast through space, time will slow down for you relative to someone who's not moving as fast.
Time slows down.
Yeah, and this isn't just some kind of like theoretical idea.
No.
This is something that's been experimentally verified.
It has.
They've done experiments with atomic clocks.
Atomic clocks, yeah.
Yeah. You know, they put one atomic clock on a plane
Mm-hmm.
and they fly it around really fast.
And another one on the ground.
Yeah, and when the plane lands, the clock that was on the plane is slightly behind the clock that was on the ground.
Slightly behind.
Yeah, because it was moving faster through space.
So time slowed down for it.
Right, and the faster you move, the more pronounced this effect becomes.
The more time slows down.
So in theory, if we could build a spaceship that could travel at a significant fraction of the speed of light,
Like close to the speed of light.
yeah, we could send someone on a journey.
Mm-hmm.
And when they came back, you know, years or even decades later,
Right.
centuries could have passed on Earth.
That's amazing.
Yeah, they would have essentially traveled to the future.
They would have.
Now, of course, the technological challenges of building such a spaceship
Right.
are immense.
Huge.
You know, we're nowhere near being able to do that right now.
Not yet.
But the physics of it,
Yeah.
the underlying science,
Mm-hmm.
that's all solid.
It checks out.
So it's at least theoretically possible.
Theoretically possible.
Now, there's a really famous thought experiment that illustrates this concept of time dilation due to relative motion.
Okay. What is it?
It's called the twin paradox.
The twin paradox. I've heard of this.
Have you? Yeah. So imagine you have two identical twins.
Okay.
One twin stays on Earth,
Okay.
and the other twin gets into a spaceship and blasts off into space at a speed close to the speed of light.
Okay. So one's on Earth, one's in space.
Right now, because the traveling twin is moving so fast through space,
Mm-hmm.
time slows down for them relative to their twin back on Earth.
So they age slower?
Yeah,
Oh.
when the traveling twin eventually returns to Earth,
Okay.
they will be younger than their twin who stayed behind.
The twin that stayed on Earth will be older.
Right, and the bigger the difference in speed,
Yeah.
the bigger the difference in age will be.
That's fascinating.
Yeah, so it's a really cool concept.
It is.
And it's a real consequence of the laws of physics. It's
Yeah.
not just science fiction.
So time travel to the future is possible.
It is, at least in theory.
And it's already happening to some degree with astronauts on the International Space Station.
Right, they're experiencing time dilation,
They are
albeit a very, very tiny amount.
tiny but measurable.
Yeah, so that's one way to travel to the future, go really, really fast.
Okay.
Now, our sources also talk about another way to travel to the future,
What's that?
and this one has to do with gravity.
Gravity. Interesting.
Yeah, it turns out that gravity also affects the flow of time.
It does.
The stronger the gravitational field,
Mm-hmm.
the slower time passes in that region.
So the closer you are to a massive object, like a planet or a star,
Yeah,
the slower time will pass for you.
exactly. So even here on Earth,
Right.
our planet's gravity is causing time to pass slightly slower
Slightly.
than it would in deep space, far away from any massive objects.
So we're actually time traveling right now compared to someone floating in deep space.
We are, although the difference is incredibly small.
Yeah, it's tiny.
It's like fractions of a second over a lifetime.
Not enough to make a practical difference.
Not really, but the principle is there.
It is.
Gravity affects time.
And the stronger the gravity, the bigger the effect.
Right. So now let's imagine a really, really strong gravitational field.
Okay.
Like the kind of field you would find near a black hole.
A black hole.
Yeah, black holes are these incredibly dense objects.
They have so much mass packed into a tiny space.
Yeah, and their gravity is so strong
It's immense.
that not even light can escape from them.
Hence the name black hole.
Right. So if you were to get close to a black hole,
Okay.
time would slow down for you dramatically
Dramatically.
compared to someone who's far away from the black hole.
Okay.
And the closer you get to the black hole, the slower time would pass.
So if you were to get really close to the event horizon,
Yeah, the event horizon is the point of no return.
point of no return.
Right. Once you cross the event horizon, you can't escape the black hole's gravity.
No, it's
So if you were to get really close to the event horizon and then somehow manage to escape,
right.
you would have essentially traveled to the future
You would have.
because time would have passed much more slowly for you than it did for the people who stayed far away from the black hole.
So you could spend a year near a black hole
Yeah,
and come back to Earth to find that 100 years had passed.
exactly. It's like a one-way time machine to the future.
It's incredible.
Yeah, so we've got two ways to travel to the future.
Oh, let's recap.
Go really, really fast
Mm-hmm.
or hang out near a black hole.
Or hang out near a black hole.
Both of these methods are theoretically possible,
They are.
but they both have some pretty serious drawbacks.
They do.
For one thing, they're both one-way trips.
One way.
You can't go back to the present once you've traveled to the future.
No round trips.
And even if we could overcome the technological challenges
Right.
of traveling at near light speeds or surviving near a black hole, there's the whole issue of being completely disconnected from your time.
You'd be leaving everyone and everything behind.
Yeah, you'd be stepping into a future that's completely alien to you.
It would be a very different world.
It would be so while traveling to the future is certainly an intriguing possibility.
It is.
It's not exactly a practical solution for getting to next week's meeting on time
Or winning the lottery.
or winning the lottery. Yeah.
So what about traveling to the past?
That's the big question, right?
That's the one everyone wants to know about.
Yeah, if we can travel to the future, can we also travel to the past?
Can we rewind time?
Can we go back and relive our glory days or, fix our past mistakes?
Or meet historical figures?
Right. So far, we've talked about how we can kind of manipulate our speed through time
Mm-hmm.
by changing our speed through space
Right.
or by being near a strong gravitational field.
Yep.
But can we use these same principles to actually reverse the flow of time?
Can we make time go backward?
That's what we're going to explore next.
Oh.
So we know that everything in the universe is moving through space-time at the speed of light.
That's our speed budget.
Right. And we know that if we increase our speed through space,
Mm-hmm.
our speed through time decreases.
Time slows down
Right. So what if we could go faster than the speed of light?
faster than the speed of light.
Yeah. What if we could break the cosmic speed limit?
That's forbidden, isn't it?
Well, according to Einstein's theory of relativity, yes.
Okay.
Nothing can travel faster than light.
Okay.
At least nothing that has mass.
Right.
But let's just for a moment entertain the possibility.
Okay. Let's break some rules.
It's break some rules.
Yeah.
What if we could go faster than light?
What would happen?
Well, the math of relativity suggests that if something were to travel faster than light,
Okay.
it would actually have to move backward in time.
Backward in time.
Yeah. It's like if you push that speed through space slider all the way past the speed of light,
Right.
the speed through time slider flips around and goes into the negative.
So you're moving backward through time.
Exactly. So this has led some physicists to speculate about the existence of particles that are always faster than light.
Always.
Yeah, they wouldn't have to start slower than light and then speed up.
Right.
They would just always exist in this superluminal state,
Superluminal.
faster than light. And these hypothetical particles have been given a name.
Okay, what are they called?
Tachyons.
Tachyons.
Yeah, it's a cool name, right?
It is.
So tachyons, if they exist,
If.
would be moving backward in time from our perspective.
Okay.
And this raises all sorts of really interesting questions about the nature of causality.
The causality.
Yeah, the relationship between cause and effect.
Because if you can move backward in time,
Yeah.
could you change the past?
Right. Could you go back in time and prevent some event from happening?
Or make something happen?
Or make something happen, and if you did, what would the consequences be?
That's a big question.
Yeah, it's a huge
A
question.
really, really big question.
And it's one that physicists have been grappling with for decades.
Yeah, it's a real head scratcher.
It is now, there's a lot of debate about whether or not tachyons actually exist.
Right.
Some physicists think it's at least theoretically possible.
While others think it's just plain impossible.
Yeah, and so far there's no experimental evidence to support their existence.
No tachyons have ever been detected.
Right, we haven't seen any evidence of particles moving faster than light.
Not a single one.
So for now, at least, the idea of tachyons and backward time travel remains purely speculative.
It's just a theory.
Yeah, it's a fascinating theory,
It is.
but it's one that's not supported by any hard evidence.
Not yet, anyway.
So it seems like the universe has some pretty strict rules about the direction of time.
It does.
We can travel to the future by moving really fast or by hanging out near a black hole.
One-way trips?
But traveling to the past?
Well,
That's a much trickier proposition.
seems to be off the table.
Yeah, it might just be impossible.
But who knows? Maybe someday we'll discover something new.
Yeah, maybe.
Something that changes our understanding of the universe.
Yeah, that would be amazing.
It would.
So in the meantime, I think it's important to appreciate the present moment.
The here and now.
Yeah, the past is gone.
It's in the past.
We can't change it.
Nope.
But the future is still unwritten.
It's full of possibilities.
Yeah, we have the power to shape the future
We do.
through our actions and our choices.
Every decision we make, every action we take, shapes the future.
Exactly. And while we might not be able to travel back in time and change the past,
Right.
we can learn from it.
We can study history.
Yeah, we can study history. We can try to understand how we got to where we are today.
And use that knowledge to make better decisions in the present.
Right. And that's really the most important thing.
It is.
It's not about dwelling on the past or obsessing over the future.
What's
It's about living in the present,
And making the most of it.
making the most of it. Yeah.
Because that's all we really have.
It is. And that's something that I think gets lost sometimes
It does.
in all this talk about time travel.
Yeah, we get so caught up in the what ifs.
Yeah, what if I could go back and do this differently? Or what if I could see what happens in the future?
But we forget to appreciate the now.
Yeah, we forget that the present moment is all we really have.
It is.
And it's precious.
It's a gift.
It is so, I think that's a good place to wrap up our deep dive into time travel.
Yeah, it's been a fascinating journey.
It has, and I want to thank you for joining me on this adventure.
I've enjoyed it.
Me too, and I hope you learned something along the way.
I certainly have.
Me too. And I hope you'll join me next time for another deep dive into the mysteries of the universe.
I'll be there.
Great. Well, until then, thanks for listening,
Thanks for having me.
and keep exploring.